Good afternoon everyone and welcome to Year 12 Physics. In class today we want to be looking at light as an EM wave, and we're going to be talking about polarization and how polarization can be used as a phenomenon to give support to the wave theory of light and to refute the particle theory of light. Polarization. Mucking around with polarization today. We're going to be mucking around with polarizing films, which look like these. I got one polarizing film, place it over my little cross, nothing happens, that's all fine and well and good. I bring in the second polarizing film, put it over the cross, and when you're actually in the classroom, you might get a chance to do this. I twist it through 90 degrees, and we see that our little cross disappears. Okay, so we'll be mucking around with those today. But before we get into polarizing films and how they can demonstrate polarization, we're going to talk about what light is. Light is an electromagnetic wave. That's what our argument is going to be today. We say that light is electric and magnetic fields leapfrogging each other through space. That's what we say they do. I've got a diagram here to illustrate this concept. Now, when we think about light being an electromagnetic wave leapfrogging itself through space, we tend to think of it in three dimensions, which can be a little bit challenging. Here I've got a light source, and for this particular light source, we see light is moving to the right of screen. The black sinusoidal wave, we're going to say that that one is an electric field. And the green sinusoidal wave, we're going to argue that the green sinusoidal wave is a magnetic field. So these two fields are leapfrogging each other through space. Don't worry about the right-hand palm rule, it doesn't matter. Okay, it doesn't matter. All that matters is that you've got the E and the B field waxing and waning. That means, getting bigger and getting smaller periodically and inspiring each other to get bigger and smaller as they leapfrog each other through space. This is looking at it from the side. If we were to look at this from the front, so if we were to look at this situation straight down the barrel, looking at the light globe, then we would see these electric and magnetic fields coming towards us. And in our field of view, that might look like, in this case, the electric field is vertical. So the electric field would be up and down, moving out of the page towards us. And the magnetic field would be a sinusoidal thing going side to side, moving towards us from out of the page. So that's what we see. Now, the light is a hot body. And in my drawing, I've got a orientation of the light coming out that appears to be polarized. It looks like the electric field is vertical and the magnetic field is horizontal. But the fact of the matter is that our hot bodies do not emit polarized light. They emit non-polarized light. So the sun, your incandescent light globe, all of these things which glow that are luminescent, they all emit non-polarized light. So we see this situation, but in reality, coming towards us out of the screen, we've got this one, and this one, and this one, and that one there, and all of the associated green vectors as well. So the light coming out of the screen is not in any way polarized. It's coming out at us with the electric field in all sorts of orientations, with many, many different orientations moving towards us. This is unpolarized light coming out towards us now. If we were to pass unpolarized light through a polarizing screen, and a polarizing screen, it's kind of easy to think about these things. It's kind of like it only permits, so we might have a polarizing screen that only permits electric fields to move through if they're in the vertical. Then as this non-polarized light goes through our polarizing screen, then it might only allow electric fields in the vertical to pass through, and that means that the magnetic fields in the horizontal pass through as well. And you might ask, how does a polarizing screen work? Okay. To get your head around how a polarizing film works, let's imagine a very long jump rope. We're going to imagine a very long jump rope. So imagine we've got ourselves a very long jump rope, and that jump rope is being moved in a spiral type fashion, and those spirals are moving towards the other end of the rope. We might say that the jump rope is not polarized. The rope itself is moving up and down and side to side and up and down as it spirals around and around and around and around. Now, if you go and place a gate, if you go and place a solid gate through here, that's going to take the jump rope. As it approaches the gate, it will be spiraling as it approaches towards the gate. But as it goes through the gate, it will be forced to only go up and down. This is taking an unpolarized jump rope and forcing it to be polarized on the way through, because the gate only allows movement of the jump rope up and down and doesn't allow movement of the jump rope side to side. This is the way a lot of teachers try to explain polarization. I'm trying to explain it. I should say, this is the way a lot of teachers explain polarization. This is how I'm trying to explain it. Hopefully I've done the job. So that's one way to think of polarization. So how does a polarizing film do the same exact thing for light? Let's have a look at that. Okay, this is symbolic of unpolarized light moving out of the board. I've got black arrows going to all the points of the compass and the minor points of the compass as well. And they're symbolic of the electric field as it moves out there unpolarized. I've not drawn in the magnetic field because it just gets too complicated with the magnetic field as well. We are interested in the unpolarized nature of the light and the behavior of the electric field as it moves out towards the viewer. I'm now going to draw a screen. One of these guys here, a polarizing screen. Now in my polarizing screen, to you and me, it looks like a bit of black plastic. It's quite flexible, it's very nice. But the polarizing screen has very long chain molecules. So many of them you can't see them. They're all very closely packed together, and there are a lot of them. Very long, closely packed molecules, chain molecules up and down the screen. In one dimension only. In this case, I've drawn them vertical. If an unpolarized light moves through this screen out of the page, any part of that unpolarized light which has electric field in the vertical will stimulate electrons within these long chains and cause them to move up and down. So I want you to imagine that there's these tiny little electrons all throughout these long chain molecules on our polarizing screen. As the unpolarized light moves through the screen, these electrons are inspired to move up and down by the vertical components of this unpolarized light. The vertical electrical components. That means that the vertical electrical components are doing work on these tiny little electrons. The horizontal components are doing no work on the electrons, which means the vertical components are consumed, and coming out the other side, since the vertical electrical components are consumed, coming out the other side, we only have horizontal components of light moving out through the other side, which means our light moving out the other side becomes polarized. In this case, the way I've drawn it, unpolarized light hits my polarizing screen where all the chains are up and down. All of the up-down vertical components of our unpolarized electrical fields get consumed, moving the electrons up and down, which means that only the horizontal components of electric field come out the other side because they were not consumed, they didn't do anything. And that means my light is now polarized with the electric in the horizontal plane.
That comes out, would the orientation of the wave be perpendicular to the filter?
The orientation of the electric part of the electromagnetic wave will be perpendicular to the long chain molecules in that film. Okay, how do we feel about that? Questions? So the question was, hey, that's great. We're looking at what happens to the electric field component of the light, which inspires movement in the loose delocalized electrons in those long chain molecules up and down, consumes the electric field. Only the horizontal field gets through. Only the horizontal components of the electric field get through. Magnetic field doesn't interact with the electrons at all.
Oh.
So this has no effect on the magnetic part of the electromagnetic light.
But because the actual light is being stored by the electric...
Yes, because the vertical components of that electric light are being consumed, okay, the vertical components of that electromagnetic light are being consumed, then only the horizontal components get through, and they inspire vertical magnetic field. remember we said that the light moves to the right horizontally, but the E and B fields inspire each other or induce each other perpendicularly. So light is, in this sense, a three-dimensional product. There's the direction it's moving, plus there's the E field in one dimension, the B field in the other dimension. So 3 dimensions there. Okay? All right. So what happens if my film is turned through 90 degrees? If I turn my film through 90 degrees, the unpolarized light approaches the film, comes out of the page. So this is, you've got to think of this as being behind the film, comes out of the page, and now the horizontal electric field components of this electromagnetic light, they will inspire movement of the delocalized electrons in those long chain molecules, and they will be consumed by that movement. So the horizontal electric field components of the electromagnetic light will be consumed, moving these delocalized electrons around inside of our film, which means only the vertical components get through in that situation, and the vertical components then induce and create magnetic components which are horizontal, and that comes out. We now have polarized light coming out of our film. So this from behind the film goes through the film, and only the vertical electric field components of the electromagnetic light get through. Alrighty. What if I have 2 films and I place them on top of each other, one with the long chain molecules horizontal and one with the long chain molecules vertical? In that situation, one of the films will consume all of the vertical E components of the EM light. The other film will consume all of the horizontal components of the EM light, and the end result is that no light will get through. Okay, now it's time for some fun. Could you please draw for me an X on your piece of paper? So this is an X on a screen. We introduce a polarizing film. The polarizing film causes the X to black out because the light coming out of my computer screen is polarized. Here comes a second polarizing film, and as we rotate it through 90 degrees, we see the X disappear, reappear, disappear. But look at this, a third polarizing film in between them has a very special magical effect. So I'm not sure if we were able to get this into the video, but we were mucking around with looking at an object on a piece of paper through 2 polarizing films where the lines on the polarizing films were perpendicular to each other. We managed to black out the object we were looking at, and that's great now. We're getting our heads around that. And that's perfectly reasonable given the wave theory of light. So once you block all of one of the dimensions of the possible E fields present in unpolarized light, and then you block all of the perpendicular E fields possible from that unpolarized light, then none of the polarized light can get through. So this gives evidence to light as a wave, where light is sinusoidal E fields and B fields moving through space. What would happen if light was a particle? If light was a particle, and these particles are really, really small, then the particles would easily fly through one film because there are little gaps between the long chain molecules in the film. And even if you brought in a second film that was perpendicular to it, there's still holes for the light to fly through, and so you should be able to still see your object on the other side of the 2 films. So when we see that the light is polarized by one set of film and then completely blacked out by the second, and yet if we twist the second through 90 degrees, suddenly it's visible again, invisible, visible, that gives evidence to the wave theory of light. It matches the wave theory of light, where E fields move through space in a sinusoidal wave-like fashion, and B fields move through space in a sinusoidal wave-like fashion. Particle theory suggests that what we've just observed should not happen, because if light were particles, it should still be able to get through the film equally, whether the films are perpendicular to each other or horizontal to each other. Now, on the topic of the third film, if we block out this unpolarized light source, I've got it drawn over here, but we've got to imagine that this is behind this, which is behind this. Okay? If this is coming out of the board, we cover it with this, we can still see it. But what we see is the polarized version of this, and given the vertical lines, we would only see the E field that comes through that is horizontal in its polarization, and the B field would be vertical in its polarization. This placed over the top of that will block the whole thing out. If we place our third film between these two, and we orientate the third film so that the long chain molecules are diagonal, in that situation, what we end up with, as the light passes through this region, we've got ourselves light that is in the... Okay, we have light that is polarized in the horizontal. As it passes through here, there are components of this light which are able to pass through. So components perpendicular to these long chain molecules. So they're able to pass through, and then components of those components are able to pass through the third piece. And so we see the unpolarized light gets polarized, but then in a diminished fashion, it gets shifted so that the components of this polarization, which are perpendicular to these long lines, passes through, and then the components of that orientation, which are perpendicular to this light, pass through, and some of the light still manages to slip through. Two of our films only, nothing slips through, but with 3 films, where that middle one is diagonal, we're able to train the light from unpolarized to polarized, and then shift the polarization, drag the polarization to the vertical. Okay, that's the end. I hope that was useful.